Module 3, Lecture A, Sequential Models. By the end of this lecture, you will be able to construct Keras sequential models with common layer types for supervised learning tasks, configure model compilation settings including loss functions, optimizers, and metrics, and train and evaluate sequential models using model.fit and model.evaluate. Building sequential models. Layer list definition. In a sequential model, you build a straight line of layers that data passes through from input to prediction. This sequence encodes your assumptions about how raw data should be transformed into useful outputs. You usually begin with layers that accept and reshape the input, then add layers that extract features, and end with layers that convert those features into predictions such as class labels or numeric values. Each layer takes a tensor, applies a transformation with an activation function, and passes the result to the next layer. This simple linear structure works well when data can be processed step by step without any branching paths. When building a sequential model, the list of layers should match your data type and prediction goal. For tabular data, you typically use densely connected layers to adjust and process feature dimensions. For images, you usually start with convolutional and pooling layers to detect visual features such as edges and shapes. For text classification, you often begin with an embedding layer to turn words into vectors, then add layers that capture word order, and finish with a dense layer that outputs class probabilities. Overall, the chosen sequence of layers reflects both domain knowledge and modeling strategy. When defining the layers of a model, you choose its depth, meaning how many layers it has, and its width, meaning how many units or filters are in each layer. Increasing depth or width lets the model learn more complex patterns, but also raises the risk of overfitting and increases computation. To control this, you can add regularization methods such as dropout or normalization at important points in the network. Designing a good sequential model is an iterative process of building, training, evaluating, and then refining it based on performance and practical limits like training time and available data. Python code, layer list definition. This script demonstrates a simple sequential model pipeline where you build a model by defining an ordered list of layers. The main idea is to understand how layers are stacked in a specific sequence to form the model. You should run the cells in order so you can follow how the model is constructed step by step. By the end, you will see how a basic sequential model is organized and executed. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this specific version helps ensure the code behaves as expected, since different TensorFlow versions can change features or introduce bugs. This command is usually run in a terminal or notebook to set up the library before running the rest of the script. We start by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we use Keras, a high-level interface that makes it easier to build neural networks. We also import the layers tools from Keras, which provide the building blocks for creating our model. With this setup, we can define and train neural networks in a more straightforward and intuitive way. This line displays the version of TensorFlow currently in use. Knowing the exact version is important because different versions can behave differently. By checking and recording the version, you help ensure that your code runs the same way across different systems and environments. We set the random seed using TensorFlow's random module so that any random numbers generated are the same every time we run the script. This makes our experiments reproducible, meaning we can reliably get identical results across different runs. Reproducibility is especially important when debugging models or comparing their performance, because it removes variation caused by randomness and lets us focus on real differences in the code or model design. We create a small batch of synthetic input data using TensorFlow's random normal function, which produces values drawn from a normal distribution. This gives us a tensor with 32 rows and 8 columns, representing 32 samples with 8 features each. Such randomly generated tabular data is useful for testing and training models when real-world data is not available or not needed. This line creates synthetic numeric target data for a regression task by using TensorFlow's random normal function. It generates a tensor with 32 rows and 1 column, meaning there are 32 target values, each represented by a single number. These values act as simulated regression targets, allowing you to test how well a model can learn. The built-in randomness helps mimic the natural variability found in real-world data. We check that the number of input samples matches the number of target samples by comparing their batch sizes, which are given by the first dimension of each dataset. This ensures that every input example has a corresponding target example. Making this check is essential because the model can only be trained correctly when inputs and targets are properly paired one-to-one. We build a sequential model as an ordered stack of layers. It starts with an input layer that takes data with 8 features, defining the input shape. Then we add a dense layer with 16 units, using a ReLU activation to introduce nonlinearity and learn complex patterns, followed by another dense layer with 8 units and the same activation to further refine these features. The model ends with a dense layer that has 1 unit and a linear activation, making it suitable for predicting a single continuous value in regression tasks. This code prints a brief summary of the model's architecture using the Keras Sequential Model Summary feature. It shows the structure of the layers, including how many parameters each layer has and whether those parameters can be trained. Nested layers are not expanded in detail, but the output clearly indicates which parameters are trainable. This summary is useful for checking that the model is configured correctly before starting training. Before training a model, we must compile it by choosing the optimizer, loss function, and evaluation metric. In this case, we use the atom optimizer with a learning rate of 0.01 to update the model's weights efficiently. We select mean squared error as the loss function, which is standard for regression because it measures the average squared difference between predictions and true values. We also track mean absolute error as the evaluation metric, giving a simple measure of how far predictions are from the actual targets on average. The model is trained using a fit function that takes input data and target values, and it runs for 5 epochs, so the model goes through the entire dataset 5 times. The batch size is set to 8, meaning the data is processed in small groups of 8 samples at a time. The verbose setting is 0, so no training progress or details are printed during this process. This configuration lets the model learn from the data quietly without showing output on the screen. The code evaluates the trained model using the same small dataset it was trained on, measuring how well it predicts the target values. It computes the loss and the mean absolute error as performance metrics. The evaluation runs silently without showing progress. This step confirms how closely the model's predictions match the actual targets. The code reports the final performance of the trained model by printing 2 key metrics. It first shows the mean squared error loss, which indicates how closely the model's predictions match the true target values. It then prints the mean absolute error, which summarizes the average size of the prediction errors without considering their direction. Together, these metrics provide a clear view of how accurate and effective the model is on the given data. This script shows how to build and train a simple neural network for a regression task using TensorFlow's Sequential API. It first fixes the random seed for reproducibility, and creates synthetic data with 32 samples, each having 8 features and corresponding target values. The model consists of an input layer, 2 hidden layers with ReLU activation, and a final output layer with a linear activation. After compiling the model with the Atom Optimizer and mean squared error loss, it is trained for 5 epochs on the synthetic data without printing intermediate output. Finally, the model is evaluated on the same data, and the mean squared error loss and mean absolute error are printed to indicate its performance on this small dataset. Specifying input shapes. When building a model, defining the input shape is essential because it tells the model how many features to expect and how they are organized. For example, a house price model with 10 attributes per house needs an input shape that represents a vector of length 10. Image models need shapes that reflect the height and width of the pixels. Language models may use shapes that describe sequences of word indices. This specification allows the framework to allocate weights properly and connect layers consistently from the beginning, ensuring the model is constructed correctly. When defining input shapes for models, you should focus on the structure of a single example and let the framework handle how many examples are grouped into a batch. For a regression task with 3 features, this means using a vector of length 3, while a color image classification task might use a 3-dimensional array that represents height, width, and color channels. In time series forecasting, the input shape needs to capture both the number of time steps and the variables at each step. Thinking this way keeps your attention on the content of each example and allows the model to work with different batch sizes and computing environments. Different neural network layers expect inputs in specific shapes based on the data and operations they use. Dense layers require flat vectors, so images or sequences often need to be flattened or embedded first. Convolutional layers, common in image and audio tasks, need spatial or temporal dimensions to be preserved, while recurrent layers need inputs that reflect sequence length and step structure for tasks like language modeling. When designing models, such as for image classification or energy use prediction, you must match your data's shape to what the first layer expects to avoid errors and keep data flowing correctly through the network. Python code. Specifying input shapes. This script demonstrates how input shapes work in Keras, focusing on simple sequential models. As you run the cells, you will see how different layers interpret and transform the input shapes. The outputs help you understand how data flows through the model and how layer configurations affect the resulting shapes. Overall, it is a practical way to visualize and confirm the dimensions of tensors at each stage of a sequential network. The script starts by noting that TensorFlow is already installed in this Colab environment. For use in other environments, it includes a commented instruction showing how to install TensorFlow version 2.20. This helps ensure you are using the correct version so the rest of the code runs properly and remains compatible. We begin by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we also import Keras, a high-level interface that makes it easier to build neural networks. In addition, we bring in the layers tools from Keras, which provide the basic components for constructing network architectures. Together, these imports prepare the environment for creating and training models in the code that follows. We set a fixed seed for TensorFlow's random number generator, so the code produces the same results every time it runs. Using a specific seed value, such as 7, makes all random operations in TensorFlow repeatable across runs. This determinism is especially helpful for debugging because it lets you reproduce issues exactly. It also allows you to fairly compare model performance between different executions of the same script. This line displays the version of TensorFlow currently in use. Knowing the exact version helps you check that your code and libraries are compatible. It also makes debugging easier, since different TensorFlow versions can change features or behavior. In short, printing the version is a quick way to confirm you are working with the expected setup. We begin by setting up some simple tabular data for our example. To do this, we first import a numerical computing library that will handle basic number operations. Next, we choose to work with 8 samples, which means our dataset will contain 8 rows. Each row corresponds to one sample, so this choice directly determines the size of the dataset we will work with. We generate a feature matrix by using a random number function from a numerical library to create data with the correct number of samples and 3 features, matching where our model expects as input. After creating this matrix, we convert the values to the float32 data type. This ensures the data is compatible with TensorFlow operations and can be processed by the model without type issues. To create target values for a regression task, we use a random number generator from a numerical library to produce an array of random values, with one target value for each sample. The shape of this array is determined by how many samples we have. We then convert these values to the float32 data type so they work correctly with TensorFlow operations. The code prints the shape of a single example from the tabular dataset to check its dimensions. This confirms that one data point has the correct number of features expected by the model. By examining the first row of the feature matrix, we verify that each sample matches the required input shape. This quick check helps ensure the data is properly formatted before training or evaluation. In Keras, a sequential model lets us stack layers in a simple linear order. We start with an input layer that expects 3 features for each example. Then we add a dense layer with 4 units that uses a ReLU activation function to introduce nonlinearity and help the model learn more complex patterns. Finally, we add a dense output layer with a single unit, which is suitable for regression tasks where we predict one continuous value. The code displays the input and output shapes of the sequential model to confirm how data flows through it. It first prints the input shape defined by the input layer, showing how incoming data must be structured. Then it prints the output shape determined by the final layer, showing the form of the data produced by the model. Together, these shapes help verify that the model is configured with the correct input and output dimensions. We begin by compiling the model to prepare it for training. We choose the Atom optimizer because it is efficient, especially when dealing with sparse gradients. For the loss function, we use mean squared error, which is appropriate for regression tasks where we want to reduce the squared difference between predicted and actual values. We also track mean absolute error as a metric, giving a simple measure of accuracy based on the average absolute difference between predictions and true values. The model is trained using a fit function that takes the input features and target values. Training runs for 5 epochs, meaning the model goes through the entire dataset 5 times. A batch size of 4 is used, so the model updates its weights after every 4 samples. The verbose setting is turned off, so no training progress messages are shown during this process. The code uses the Keras evaluate function to measure how well the trained model performs on a given dataset. It takes the input features and target values, runs the evaluation silently, without showing progress, and returns 2 metrics. These metrics are the loss and the mean absolute error, which are stored for later use. Together, they indicate how accurately the model fits the data. The code reports the model's performance after training by printing the final loss and the mean absolute error from the evaluation step. It converts these values to simple numeric form before displaying them. This gives a clear, concise summary of how well the model performed. This script shows how to define input shapes in Keras using a simple sequential model for a regression task. It creates a small synthetic dataset with 8 samples and 3 features each, then builds a model whose input layer matches this feature shape, followed by 2 dense layers. The script prints the model's input and output shapes to confirm the architecture, compiles it with the atom optimizer and mean squared error loss, and briefly trains on the dummy data. Finally, it evaluates the model and reports the loss and mean absolute error to give a quick sense of performance on the synthetic dataset. Reading Model Summary. When you build a model in Keras, using the summary feature is an important way to check that the model matches your intentions. The summary shows each layer's name, type, output shape, and number of trainable parameters, so you can confirm the sequence of layers and how the dimensions change. This helps you spot mistakes such as missing activation functions or incorrect numbers of units. It also lets you verify that the final output shape is appropriate for your prediction task, whether you need a single value, a probability distribution, or a vector of scores. The output shape column in a model summary shows how data changes as it passes through each layer. For image models, it should reflect the height, width, and number of channels at the input, then how spatial dimensions shrink and channels grow through convolution and pooling. For tabular classification, it shows how an input feature vector is transformed by dense layers into higher dimensional representations and finally reduced to match the number of classes. By comparing these shapes to your planned architecture, you can quickly spot problems such as unexpected dimensions or incompatible layer outputs. The number of parameters in a model summary is important because it reflects the model's capacity, how much computation it requires, and its potential to overfit. Each layer's trainable parameters are listed, and the total at the end shows whether the model is lightweight or very large. Smaller models, like simple regression, have far fewer parameters than deep networks for tasks such as medical imaging, which may need more regularization in data. By examining these counts, you can make informed design choices, such as changing dense layers or simplifying convolutional parts. Python code, reading model summary. This script demonstrates a simple sequential model and how to interpret its summary. It highlights how to read the shapes of each layer and understand the number of parameters involved. By running all the cells, you will see a concise printed summary that focuses on these key aspects of the model structure. The commented line recommends installing TensorFlow version 2.20.0 to match the code being used. Specifying this exact version helps avoid problems caused by differences in features or syntax between releases. This practice keeps the software environment consistent and reduces unexpected errors when running the code. We begin by importing TensorFlow, the powerful library used for machine learning and deep learning. This gives us access to many built-in tools for constructing, training, and evaluating models. It also includes Keras, a high-level interface that makes it easier to build and train neural networks. By importing TensorFlow, we can efficiently use all of these capabilities in our projects. We begin by printing the TensorFlow version being used, which helps us understand the exact environment where the code is running. This information is important for compatibility, because different versions can change features or behavior. It is also useful when debugging or sharing code with others, so everyone can match the same setup and avoid version-related issues. We set the random seed in TensorFlow to a fixed value, such as 42, so that any random operations produce the same results every time the code runs. This makes our experiments reproducible, meaning we can reliably repeat them and get consistent outcomes. Reproducibility is especially important when debugging models or comparing their performance across different runs. To create a small dummy dataset for demonstration, we start by importing the numerical computing library NumPy. This library is important because it lets us create and manipulate arrays efficiently. We will use these arrays to simulate the data that our model will work with. In short, NumPy provides the basic tools we need to build and handle the example dataset. We start by creating a small feature matrix using a random number generator, producing 10 data samples with 8 features each. After generating this matrix, we convert its values to the float32 data type. This conversion is important because it ensures the data will be compatible with TensorFlow operations used later in the script. We generate a small target vector for binary labels by using a random integer function to create values of 0 or 1 in a 10 by 1 array. After creating this array, we convert it to a 32-bit floating point type. This conversion ensures the data will be compatible with TensorFlow operations used later in the workflow. Before building a model, we must confirm that the number of samples in the feature matrix matches the number of samples in the target vector. This ensures that every input example has a corresponding target label. By checking that the first dimension of both arrays is the same, we verify that the data is properly aligned. This simple step helps prevent errors and mismatches during training. To build a simple classification model, we start by using the sequential model from the Keras module in TensorFlow. This lets us stack neural network layers in a straight line where each layer passes its output to the next. We also import the collection of layer types from Keras so we can choose the ones we need. Together, these tools let us define a clear, step-by-step architecture for a neural network that is easy to build and understand. We build a neural network using a sequential model, adding layers one after another. The network starts with an input layer that takes data with 8 features. Then we add a dense layer with 16 neurons using a ReLU activation to introduce nonlinearity, followed by another dense layer with 8 neurons that also uses ReLU. Finally, we add a dense output layer with a single neuron and a sigmoid activation, which produces values between 0 and 1 and is suitable for binary classification. We begin by printing a clear title to indicate that the output that follows is the summary of our sequential model. This simple step helps organize the console or log output and makes it easy to quickly spot and identify the model summary among other messages. By labeling the summary clearly, we improve readability and make later review or debugging more efficient. The summary function of the model provides a detailed overview of the neural network's architecture, listing each layer, its type, output shape, and number of parameters. This information helps you quickly check that the model is built as intended and that the flow of data through the layers makes sense. It is especially useful for confirming that input and output dimensions match your expectations, and for getting a sense of the model's overall complexity. To train the model, we first compile it by choosing how it will learn from data. We use the Atom optimizer, which is a common and efficient method for updating the model's parameters. The loss function is binary cross-entropy, which is appropriate for binary classification because it measures how far the predictions are from the true labels. We also track accuracy as a metric, so we can see in a simple way how well the model is performing during training and testing. We train the model using the fit method, which takes the feature matrix and target values as inputs. We set the number of epochs to 5, so the model goes through the entire dataset 5 times. The batch size is 2, meaning the model updates its weights after every 2 samples. The verbose setting is 0, so training runs without printing progress, keeping the console output minimal. The code evaluates the trained model using the dummy feature matrix and target vector to measure its performance. During this evaluation, it computes the loss and accuracy on the given data. The process runs silently without printing any intermediate output. This step confirms how well the model has learned from the dataset after training. At the end, the script reports how well the model performed by printing its loss and accuracy after evaluation. It converts these values to simple floating point numbers for clarity. The script then displays them in a short message, giving a quick summary of the model's performance on the dummy dataset. This script builds and trains a simple neural network using TensorFlow's sequential model on a small dummy dataset for binary classification. It creates 10 samples with 8 features each and binary labels, then defines a network with 2 hidden layers using rectified linear activation and an output layer using a sigmoid activation. After compiling the model with the atom optimizer and binary cross-entropy loss, it trains for a few epochs and prints a summary of the layer structure and parameter counts. Finally, it evaluates the model on the same data and reports the loss and accuracy to give a quick sense of its performance on this tiny example. Configuring Keras layers, designing dense and dropout layers. Dense layers in a neural network connect every input to every output, allowing the model to learn complex combinations of features. The number of units in a dense layer controls how much the model can represent. More units increase its ability to capture subtle patterns, but also raise the risk of overfitting and memorizing the training data. When modeling tasks like predicting house prices from features such as size and neighborhood, you must choose enough units to learn useful relationships without making the model too complex. Overall, designing these layers is about balancing expressiveness and simplicity so the network generalizes well to new data. Dropout layers work with dense layers by randomly turning off some units during training so the network does not over-rely on specific connections. This effectively creates many different subnetworks inside one model, improving generalization in a way similar to an ensemble. The dropout rate is chosen based on how much the model tends to overfit and how much data you have. For example, in sentiment analysis, dropout helps the model avoid memorizing particular phrases and instead learn broader patterns. It is important to set the dropout rate high enough to regularize the model, but not so high that it prevents the dense layers from learning stable representations. Designing dense and dropout layers is an iterative process that depends on task complexity, dataset size, and available computing power. For simpler problems, you can begin with a few dense layers and little dropout, then adjust based on validation performance. For more complex tasks, such as customer churn prediction or image classification, you typically use several dense layers with gradually fewer units and increase dropout in deeper layers to reduce overfitting. The overall goal is to balance the expressive power of dense layers with enough dropout so the model learns patterns that generalize to new data instead of memorizing the training set. Python code, designing dense and dropout layers. This material introduces a simple neural network model that uses dense layers together with dropout layers. It explains how to build the model step by step using a sequential structure. The focus is on how these layers are configured and how the overall model is compiled for training. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0, not a piece of Python code. It makes sure that this exact version of TensorFlow is available before the script runs. This matters because different TensorFlow versions can change features and behavior. By specifying the version, you help keep the code consistent and compatible with the environment. We begin by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We also import the layers tools from Keras, which provide different building blocks for constructing a neural network. These imports give us the essential components needed to define and train our model in the rest of the script. We start by importing NumPy for numerical computations and then set its random seed to the value 7 so that any random numbers it generates are the same each time we run the code. We also set the random seed for TensorFlow to 7, which makes TensorFlow's random operations reproducible. Using the same seed in both libraries ensures consistent and comparable results across different runs, which is important for debugging and evaluating model performance. This line of code displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because it affects compatibility with other tools and can help when diagnosing and fixing issues. We create a small synthetic dataset to use for a classification task. It contains 200 data points, which is the total number of samples. Each data point has 10 features, meaning 10 attributes describe it. The dataset has 2 classes, so it is a binary classification problem where each point belongs to one of 2 possible categories. The code uses a random number generator to create a 2-dimensional array of input features, with the number of samples and features defined earlier in the script. These values are drawn from a standard normal distribution, so they are centered around 0 and follow a typical bell-shaped curve. After generating the data, the array is converted to the float32 data type to reduce memory usage and improve computational efficiency, which is a common practice in machine learning workflows. We use a random integer function from a numerical library to generate class labels for our data. This function produces an array of random integers, where each integer stands for a different class. The total number of labels created is controlled by the number of samples, and the range of possible label values is set by the number of classes. This approach lets us simulate a classification problem by assigning each sample a random class label from the available options. Before building the model, the code first checks that the input data has the correct shape. It uses assertions to confirm that the feature matrix contains 200 samples with 10 features each, and that the label array also has 200 entries. This quick validation step helps detect any mismatch in data dimensions early and prevents errors later during model training. We start by choosing a training set size of 160 samples, which means these examples will be used to teach the model. Since there are 200 samples in total, the remaining 40 are used as the test set. This split ensures that some data is kept separate for evaluating how well the trained model performs on new, unseen examples. To prepare the training data, we take a slice of the input features from the beginning up to the chosen training size, creating the subset used to train the model. We slice the labels in exactly the same way, so each feature set matches the correct label. Because this slicing is deterministic, the same data is selected every time the code runs, which supports reproducible and consistent training results. We create our test dataset by slicing the feature array from the training size index to the end, so only the remaining data is used for testing. We slice the labels in the same way, so each test feature has a matching test label. This deterministic split keeps the test set completely separate from the training set. As a result, we can fairly evaluate how well the model performs on data it has not seen during training. In Keras, a sequential model lets you build a neural network by stacking layers one after another in a simple linear order. Each layer takes a single input and produces a single output, which then feeds into the next layer. This design makes it easy to add and configure layers step by step. Because of its simplicity, the sequential model is especially useful for beginners and for quickly prototyping neural network ideas. We begin by adding a dense layer with 32 units, meaning it has 32 neurons. This layer uses the ReLU activation function, which introduces nonlinearity so the model can learn more complex patterns. We also specify the input shape as the number of features, which tells the model what form of input data to expect. We add a dropout layer to the model that randomly sets about 30% of the input units to 0 during training. This randomness helps prevent the model from relying too much on any single feature or small group of features. As a result, the model is pushed to learn more robust patterns that are less likely to overfit and that generalize better to new unseen data. We now add a second dense layer to the model with 16 units, fewer than in the previous layer. This layer further processes the data using a smaller set of neurons, so the model can learn more abstract features. We again use the ReLU activation function to introduce nonlinearity, which helps the model capture more complex patterns in the data. We add a dropout layer to the model with a rate of 0.5, meaning that during training, about half of the neurons in this layer are randomly set to 0 at each update. This reduces the chance that the model will depend too much on any single feature or group of features. Placing this dropout layer after a deeper dense layer strengthens regularization, which is especially helpful for controlling overfitting in more complex models. We now add the final dense layer to the model, which has a single unit designed for binary classification. This layer uses the sigmoid activation function to produce outputs between 0 and 1. Because these outputs can be interpreted as probabilities, the model can estimate how likely each input belongs to one of the two classes. This setup enables clear, probability-based predictions for binary outcomes. We use the binary cross-entropy loss function from Keras because it is well suited for binary classification problems, where the model must distinguish between two classes. This loss function compares the true labels with the predicted probabilities and measures how different they are. By quantifying this difference, it tells us how well the model is performing during training and guides the optimization process to improve its predictions. We use the Atom optimizer from Keras because it is efficient and adapts well when training neural networks. The learning rate is set to 0.001, which is a common starting value. This rate provides a good balance between learning quickly and keeping training stable. Together, these choices help the model converge effectively during training. The code creates a list of metrics that includes accuracy, which tells the model to track how often it correctly predicts the classes. During both training and evaluation, this accuracy metric is calculated and reported. Monitoring accuracy in this way helps you see how well the model is performing at its classification task over time. Compiling the model sets up how it will be trained by choosing the optimizer, loss function, and evaluation metrics. The optimizer, here the Atom method with a set learning rate, controls how the model's weights are updated during training. The loss function, binary cross-entropy, measures how well the predictions match the true labels in a binary classification task. The metric, accuracy, tracks how often the model's predictions are correct. Together, these choices configure the model so it is ready to be trained and evaluated. The model is trained using the Keras fit method, which takes the input features and labels and runs the learning process for a set number of epochs. In this case, it trains for 10 epochs, meaning it goes through the entire training dataset 10 times. The batch size is 16, so the model updates its weights after every group of 16 samples. The verbose setting is 0, which turns off detailed training messages, so the console only shows the final results instead of step-by-step updates. After training, the model is evaluated on the separate test data that was set aside earlier. The evaluation function takes the test inputs and their true labels and runs quietly without showing progress. It returns two key numbers: the loss, which measures the model's error, and the accuracy, which measures how many predictions are correct. These values indicate how well the model generalizes to data it has not seen before. This code prints a brief summary of the model's main configuration choices. It reports the loss function being used, which is binary cross-entropy, and the optimizer, which is atom. It also shows the metrics tracked during training, in this case, accuracy. Together, these printed values provide a quick check of the key components of the model setup. The code reports how well the model performs on unseen data by printing the test loss and test accuracy. It converts each value to a float, rounds it to 4 decimal places, and displays it with a clear label. The test loss shows how far the model's predictions are from the true values, while the test accuracy shows how often the model predicts correctly. Together, these rounded values give a quick, readable summary of the model's performance on the test set. This script shows how to build and train a simple neural network for binary classification using TensorFlow and Keras. It creates a small synthetic dataset with 10 input features and random binary labels, then splits it into training and test sets. The model is a sequential network with 2 dense layers using ReLU activation, each followed by dropout to reduce overfitting, and a final dense layer with a sigmoid activation to output a probability. It is compiled with binary cross-entropy loss, the atom optimizer, and accuracy as the evaluation metric, then trained for 10 epochs with a moderate batch size. After training, the script evaluates the model on the test data and prints the TensorFlow version, the loss function, optimizer, metrics, and the resulting test loss and accuracy. Keras activation functions. Activation functions in a sequential model are essential because they transform each neuron's weighted input into an output that can capture complex, nonlinear patterns. In Keras, you choose these functions based on the type of prediction task and make sure they match how you compile the model. For example, a linear activation works well for predicting continuous values like house prices, while a sigmoid activation is better for binary classification tasks such as spam detection. These choices directly influence the loss function and evaluation metrics, so understanding them is important for your model's performance. In a sequential model, activation functions in the hidden layers control how information and gradients flow during training, which affects both speed and performance. Rectified linear units are commonly used in dense layers because they are simple, efficient, and help reduce vanishing gradients in deep networks. However, they can cause some neurons to stop learning when their outputs become 0, so variants like leaky rectified linear units or smoother functions like hyperbolic tangent may work better in certain cases. Choosing and configuring these activations in Keras directly shapes each layer's capacity and influences how effectively the optimizer and loss function work together during training. The activation function in the output layer must match the loss function and metrics you use so the model's predictions are meaningful. For binary classification, such as fraud detection, a sigmoid output that produces probabilities pairs well with binary cross-entropy loss. For multi-class problems like digit recognition, a softmax output that forms a probability distribution works with categorical cross-entropy. For regression tasks, such as forecasting sales, a linear output that allows any real value fits losses like mean-squared error. Aligning these choices helps the model learn correctly for your specific problem type. Python code Keras activation functions. This script demonstrates how different activation functions are used in Keras, with a particular emphasis on the activation applied to the output layer and how it ties into model compilation. It highlights how choosing the right output activation affects the model's behavior and performance. To keep experiments fast and simple, it uses very small synthetic datasets, so the code runs quickly while illustrating these core ideas. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Specifying this exact version makes sure the script uses the intended library and avoids problems caused by changes in newer or older releases. This kind of version pinning is common in data science projects to keep behavior consistent across different systems and environments. We begin by importing several key libraries needed for our work. The operating system library lets us interact with files and environment settings. The random library provides controlled random number generation, which helps make results reproducible. We then import NumPy for efficient numerical computations with arrays. Finally, we bring in TensorFlow, which we will use to build and train our machine learning models. We set a fixed seed value of 7, so the code behaves the same way every time it runs. This seed initializes the random number generator in Python's random module, so the random values it produces are repeatable. We also set the seed for NumPy's random number generator, which controls randomness in NumPy operations, and for TensorFlow's random number generator, which affects randomness in TensorFlow computations. Using these fixed seeds makes the entire process deterministic and is essential for reproducibility when debugging or comparing model performance. This line displays the version of TensorFlow that is currently in use. It provides a quick way to check which release of the library is loaded. Knowing the exact version is important because different versions may behave differently. This helps with ensuring compatibility and makes debugging easier. The code uses TensorFlow to check whether any physical graphics processing units are available. It turns this check into a simple true or false value to see if at least one GPU is present. If a GPU is found, it sets the device type to GPU. Otherwise, it falls back to using the CPU. This approach lets the program automatically take advantage of GPU acceleration when possible to improve performance on heavy computations. This code checks whether any physical graphics processing units are available, and then prints a message stating which type of device the program will use. If at least one graphics processor is found, it selects a GPU. Otherwise, it falls back to a CPU. Knowing which device is being used helps you understand the computational resources available, which is especially important in machine learning tasks where GPU acceleration can greatly speed up processing. We create a small synthetic dataset for a regression task by first choosing 200 samples. We then generate input features as numbers evenly spaced between -1 and 1, and reshape them into a single column. To make the data more realistic, we add random noise drawn from a normal distribution and scaled by 0.1. This noise is also reshaped into a column, so it aligns with the input features, giving us slightly varied data points that better mimic real-world conditions. We define the regression targets using a simple linear relationship. Each target value is created by taking the corresponding input value, multiplying it by 3, and then adding 0.5. To make the data more realistic, we also add a small random noise term. This noise introduces variability, so the data does not follow the linear pattern perfectly, similar to what happens in real-world measurements. To build a small dataset for binary classification, we start by creating 200 evenly spaced numbers ranging from -2 to 2, and reshape them into a single column to match the model's input format. We then generate random noise from a normal distribution, scaled by 0.3, and add it to these values. This added noise introduces variability and helps the dataset better reflect real-world conditions. The code generates binary labels by adding noise to the input data and then checking whether each noisy value is greater than 0. This comparison produces a set of true or false values, forming a Boolean array. That array is then converted to numeric values in the float32 format. This conversion is needed because the model requires numerical labels, not Boolean values, for training. Before building the models, the code checks that the input and target data for both the regression and binary classification tasks have matching shapes. This ensures the data is correctly aligned, which is essential for effective learning. One check confirms that the regression inputs and targets match, and another does the same for the classification data. These assertions help catch shape mismatches early and prevent errors during model training. We build a sequential model in Keras by stacking layers in order. The model starts with an input layer that takes one feature per sample. We then add a dense layer with 8 neurons and a ReLU activation function to learn patterns from the data. Finally, we add a dense output layer with 1 neuron and a linear activation function, which is suitable for regression tasks where we predict a continuous value. We compile the regression model using the Atom optimizer, which is chosen for its efficiency and adaptability. The learning rate is set to 0.01 to balance how quickly the model learns with how stable training remains. For the loss function, we use mean squared error, a standard choice for regression, because it measures the average squared difference between predictions and actual values. We also track mean absolute error as an additional metric, which reports the average absolute difference between predicted and true targets to give another view of model performance. The model is trained using a fit procedure that adjusts its weights based on the input data and corresponding target values. Training runs for 40 epochs, meaning the model passes through the entire dataset 40 times. It uses a batch size of 16, so the weights are updated after every group of 16 samples. The training runs silently with no progress printed, and 20% of the data is held out to check the model's performance during training. The code evaluates a regression model using the full dataset by computing 2 key metrics, the overall loss and the mean absolute error. It calls the model's evaluation function with the input features and target values, and runs silently without showing progress messages. The resulting loss and error values are stored separately, so they can be used later to analyze or report how well the model is performing. We build a simple Keras sequential model for binary classification by starting with an input that takes a single feature, then adding a dense layer with 8 neurons that uses the ReLU activation to introduce nonlinearity. After that, we add a final dense layer with 1 neuron that uses the sigmoid activation. This last layer outputs values between 0 and 1, which can be interpreted as probabilities for the 2 classes. Together, this structure makes the model suitable for binary classification tasks. The binary classification model is compiled using the Atom optimizer with a learning rate of 0.01 to efficiently update its weights during training. It uses binary cross-entropy as the loss function, which measures how different the predicted labels are from the true binary labels. The model's performance is tracked with accuracy, indicating the proportion of predictions that correctly match the actual labels. This code trains a binary classification model using a Keras training function that adjusts the model's weights based on input data and target labels. Training runs for 40 passes over the dataset, and the model updates its weights after every group of 16 samples. The training runs silently with no progress printed to the console. In addition, 20% of the data is held out during training to serve as validation data, which is used to monitor the model's performance and detect overfitting. The code checks how well the binary classification model performs on the full dataset by running the model's evaluation function with the input data and their labels. The evaluation runs silently, without showing progress messages. It returns two key results: the loss, which measures how large the model's errors are, and the accuracy, which shows how often its predictions match the true labels. These two values are then stored for later use. The code first reports the setup and performance of a regression model, noting that it uses a linear output activation and mean squared error as its loss. Then prints the resulting loss and mean absolute error. It then does the same for a binary classification model, explaining that this model uses a sigmoid output activation and binary cross-entropy as its loss, followed by its loss and accuracy values. Together, these printed results give a quick overview of how each model is configured and how well it performs on the data. This script shows how to use different Keras activation functions in TensorFlow for regression and classification. It first builds a simple regression model with a linear activation in the output layer, trains it on synthetic data with a linear pattern, and evaluates it using mean squared error and mean absolute error. It then creates a binary classification model with a sigmoid activation in the output layer, trains it on data with binary labels, and evaluates it using binary cross-entropy loss and accuracy. The script also sets random seeds for reproducibility and automatically uses a graphics processor if one is available, providing a clear demonstration of how activation functions and loss metrics differ between regression and classification tasks in Keras. Weight initialization and regularization. In a sequential model, how you initialize the weight strongly influences how efficiently and quickly the model learns. Weight initialization means choosing the starting parameter values before training, and poor choices can cause activations to explode if weights are too large, or make learning very slow or stuck if they are too small. Modern initialization methods are designed to keep information flowing steadily through the layers so signals do not vanish or blow up. In Keras, selecting an initializer is essentially choosing a good starting point for optimization, which improves the chances of reaching a useful solution efficiently. In Keras, choosing the right weight initializer is an important part of setting up a model because it needs to match the activation functions and network depth. For hidden layers that use ReLU, you typically pick an initializer that keeps the activation variance stable across layers to support deep learning. Sigmoid and hyperbolic tangent activations often need different initializers to avoid early saturation. In most cases, you rely on the default initializer suited to your activation choice, and only change it for special situations, such as very deep networks, because good initial values help the model learn effectively, while poor ones can make training unstable. Regularization controls how complex a model becomes during training by adding small penalties to large weights, which encourages simpler models that generalize better. Methods such as L1 and L2 penalties can be applied to specific layers in Keras, so you can limit overfitting in large layers while keeping smaller ones more flexible. This is especially important in areas like medical diagnosis, where data is limited and models must avoid memorizing noise. When combined with good weight initialization, regularization helps models train reliably and perform well on new, unseen data. Python code, weight initialization, and regularization. This script demonstrates how weight initialization and regularization influence model training. It uses a very small dataset, so the effects can be seen quickly. As you listen, focus on how different layer configurations and settings change the training behavior and outcomes. The line with the exclamation mark is a command to install TensorFlow version 2.20.0, which helps ensure the script uses the expected library version for compatibility and reproducible results. Because this line is commented out, it does not run automatically. Instead, it serves as a reminder or suggestion for the user to manually run this installation command in their own environment if needed. We begin by importing TensorFlow and NumPy, which are the main tools we use for this script. TensorFlow provides the structure for defining and running neural network computations with tensors, while NumPy handles fast numerical operations and array manipulations. Together, they form the foundation for creating datasets, setting up model weights, and applying regularization methods in our neural network workflow. We begin by setting fixed random seeds for both TensorFlow and NumPy so that any random operations they perform give the same results every time the code runs. Using a constant seed value, such as 7, makes the behavior of the code reproducible. This reproducibility is important for debugging and for fairly comparing model performance across different runs. This line of code displays the version of TensorFlow currently in use. It provides a quick check that the intended version of the library is installed and active. Confirming the version helps ensure that the rest of the code will run correctly and remain compatible with the library. We create a small synthetic dataset to illustrate a regression task. The dataset contains 200 samples, meaning there are 200 data points. Each data point has 10 input features. This setup provides a simple, manageable regression problem that is suitable for quick experimentation and demonstration. We create random input features by using a numerical library to generate an array whose size is set by the number of samples and features, with each entry drawn from a standard normal distribution. After generating this data, we convert the values to 32-bit floating point format. This specific data type is commonly required for efficient and compatible computation in TensorFlow. We start by defining the true weights for our synthetic dataset. To do this, we generate a simple sequence of numbers beginning at 1 and continuing up to the total number of features, with each number serving as the weight for a corresponding feature. We store these values using the float32 data type, so they work efficiently and correctly with TensorFlow operations. This setup gives us a clear, consistent set of true weights to use when testing our models. To compute the target values for our dataset, we take a dot product between the input features and the true underlying weights, which gives a linear combination of the features. We then add a small amount of random noise drawn from a normal distribution and scaled down so it only slightly perturbs the values. This noise prevents the targets from being perfectly linear and better reflects real-world variability. Finally, we convert the result to a 32-bit floating point format to keep it consistent with TensorFlow's data handling. We define our training set to contain 160 samples, which lets us split the dataset into training and testing parts. The first 160 samples are used as training features, and all remaining samples become the test features. This way, the model learns from one portion of the data and is evaluated on a separate, unseen portion. Using this split is essential for measuring how well the model is likely to perform on new data. We split the target values into training and testing sets to match how we split the input features. The first part of the target array, up to the chosen training size, becomes the training targets and aligns with the data used to fit the model. The remaining values form the testing targets, which correspond to the unseen data. This separation lets us fairly evaluate how well the trained model generalizes to new, unseen examples. We first check the shapes of the training data and target labels to confirm they match what we expect. This quick verification helps ensure the data has been split correctly and is in the right format. By doing this before building the model, we reduce the chance of running into shape mismatches or related errors during training. We check the shapes of the test data arrays to make sure they match what we expect. This simple step helps catch any problems with mismatched dimensions before we build or run the model. By confirming the sizes of both the input features and the target values, we ensure the data is correctly structured for evaluation and reduce the risk of shape-related errors later on. We define a model using TensorFlow's Sequential API, which lets us stack layers in order. The first layer is a dense layer with 16 units and a ReLU activation, and it expects inputs that match the number of features in our data. The second layer is another dense layer with a single unit and no activation function, making the model suitable for regression. By default, the layers use the Glorot uniform initializer, which works well with ReLU activations by keeping the weights well balanced. The model is compiled using the Atom optimizer, chosen for its efficient and adaptable training of neural networks. It uses a learning rate of 0.01 to balance training speed and stability. The loss function is mean squared error, which is appropriate for regression because it measures the average squared difference between predictions and actual values. Mean absolute error is also tracked as a performance metric to give a clear sense of prediction accuracy. With these settings, the model is ready to be trained. To build a model with He initialization and L2 regularization, you use the He normal initializer provided by TensorFlow. This initializer is designed for layers that use ReLU activations and helps keep the weight values well scaled during training. By setting the initial weights this way, the model can learn more efficiently, while L2 regularization controls the size of the weights. We set up an L2 regularizer in TensorFlow with a penalty factor of 0.01. This regularizer adds a small extra cost to the loss function when the model's weights become large. By discouraging large weights, it helps reduce overfitting and encourages simpler models. As a result, the trained model is more likely to generalize well to new, unseen data. We build a simple neural network using a sequential model, which stacks layers in order. The first layer is a dense layer with 16 neurons that uses the ReLU activation function to capture nonlinear patterns. Its weights are initialized with the He normal method, which is well suited for ReLU, and it uses L2 regularization to discourage very large weights and reduce overfitting. The input shape matches the number of features in the dataset, so the model knows what kind of data to expect. The second and final layer is another dense layer with a single neuron, which is appropriate for predicting one continuous value in a regression task. The model is compiled using the Atom optimizer with a learning rate of 0.01 to efficiently update its weights during training. It uses mean squared error as the loss function, which is appropriate for regression because it measures the average squared difference between predicted and actual values. Mean absolute error is also tracked as a metric to show the average absolute difference between predictions and true values. With these settings, the model is ready to be trained. We begin by building two models so we can compare their performance. The first is a default model that uses the Glorot uniform initializer and serves as our baseline. The second is a regularized model that uses He initialization along with L2 regularization to improve training stability and reduce overfitting. With both models in place, we can evaluate how these different initialization and regularization choices influence overall model performance. We train the model using TensorFlow's fit method with the training inputs and targets. The model runs for 30 epochs, meaning it goes through the entire training set 30 times. A batch size of 16 controls how many samples are used before updating the model's weights. Training output is silenced by turning off verbose logging, and 20% of the training data is held out to validate the model's performance during training. We train the regularized model using the fit method, running it for 30 passes over the training data. The model processes the data in batches of 16 samples, updating its weights after each batch. Training logs are turned off so no progress messages are shown. We also reserve 20% of the training data for validation, which lets us monitor how well the model performs on data it has not directly learned from during training. We start by evaluating the default model on the test dataset using its evaluation function, which computes two key metrics, loss and mean absolute error on the test inputs and targets. The evaluation is run in silent mode, so it does not print detailed progress. The loss value represents the mean squared error, while the second value is the mean absolute error. These two results are stored for later use when we compare how well the model performs. We now evaluate the regularized model on the test dataset by running its evaluation procedure, which calculates the loss and the mean absolute error for the test inputs and targets. This evaluation is performed silently, with no progress messages shown. The resulting test loss and mean absolute error are stored for later use. These stored values allow us to compare how well the regularized model performs relative to the default model. This code prints a brief summary of how the default model performs on the test data. It reports the mean squared error, which is a standard measure for judging regression models. The error value is rounded to 4 decimal places to keep the result clear and precise. We calculate and print the mean absolute error for the default model, rounding it to 4 decimal places for clarity. This value shows the average size of the prediction errors on the test data. By examining this single number, we get a clear sense of how well the default model is performing. We report the mean squared error of the regularized model on the test data, rounding the value to 4 decimal places for clarity. Mean squared error measures how closely the model's predictions match the actual values. A lower mean squared error indicates that the model is performing better on the test set. We calculate and display the mean absolute error of the regularized model on the test data, rounding the value to 4 decimal places for clarity. This metric tells us the average size of the prediction errors the model makes on unseen data. By examining this rounded error value, we can directly compare the performance of the regularized model to that of the default model. This script shows how weight initialization and regularization affect training a simple neural network in TensorFlow. It uses a small synthetic dataset with several input features and a noisy linear target, split into training and testing sets. One model uses default settings, while another uses He initialization and L2 regularization to limit weight size. Both are trained with the Atom optimizer and mean squared error loss, then evaluated on the test data. The regularized model usually generalizes better, achieving lower mean squared error and mean absolute error, which demonstrates the value of careful initialization and regularization in neural network training. Compile, train, evaluate. Selecting loss and metrics. When setting up a model for training, choosing the right loss function is essential because it is what the optimizer tries to minimize. The loss must match the structure of your prediction target and the types of errors you care about most. For binary classification, such as fraud detection, you want a loss that punishes confident wrong predictions more than uncertain ones. For multi-class problems, like digit recognition, you need a loss that can handle several classes and increase the probability of the correct one. For regression tasks, such as predicting house prices, the loss measures how far predictions are from actual values and can be chosen to focus either on average errors or on large outliers. Metrics describe how you monitor and interpret a model's performance during and after training. While the loss function drives the optimization process, metrics provide summaries that match your domain needs. In classification, accuracy is common, but can be misleading with imbalanced classes, so precision, recall, or the F1 score may give a clearer view. In regression, measures like mean absolute error or root mean squared error are often easier to interpret because they use the same units as the target. Choosing metrics that reflect real-world priorities makes model results more meaningful and supports better decisions. When designing a model, your loss function and evaluation metrics do not have to be the same. You can choose a loss function mainly for good optimization behavior, such as being smooth and easy to train with. At the same time, you select metrics that capture real-world impact, like financial risk in credit scoring or sensitivity in medical imaging. This way, training remains efficient, while the metrics you monitor stay aligned with your practical goals, balancing technical performance with meaningful outcomes. Python code. Selecting loss and metrics. This script demonstrates how to choose and use different loss functions and evaluation metrics when training a model. It works with a very small dataset, so the training process runs quickly. The main goal is to show the full workflow of building a sequential model, compiling it with specific losses and metrics, training it, and then evaluating its performance. The line starting with an exclamation mark is a command to install TensorFlow version 2.20.0. Specifying this exact version makes sure the code runs with the expected behavior and remains compatible with the rest of the project. Different TensorFlow versions can change features or remove older ones, so fixing the version helps avoid unexpected issues. This kind of version control is a common way to keep machine learning environments consistent. We begin by importing three key tools. The operating system module lets our program interact with the computer's operating system. The random module gives us functions to generate random numbers and make random choices. Finally, we import the numerical computing library NumPy, which we will use to work efficiently with arrays and perform mathematical operations. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras, a high-level interface that makes creating neural networks easier. From Keras, we import the Layers module, which lets us add different kinds of layers, such as dense or convolutional layers, to define the structure of our neural network model. We begin by setting a seed value of 42, so that any random operations give the same results every time the code runs, which is important for reproducibility. We apply this seed to the random module, to the random number generator in NumPy, and to TensorFlow's random operations. Using the same seed across these libraries keeps experiments consistent and makes results easier to compare and repeat. This line displays the version of TensorFlow currently being used in the script. It provides a quick check that the correct version of the library is installed and running. Confirming the version helps ensure compatibility and that all features and functions work as expected. The code uses Keras to load the MNIST dataset, a standard collection of handwritten digit images used in machine learning. This dataset is automatically split into a training set with images and labels and a separate test set with its own images and labels. The model learns patterns from the training data and is then evaluated on the test data. This separation allows us to measure how well the model performs on new, unseen examples. To speed up training, we work with a smaller portion of the dataset instead of using all available samples. We set the training set size to 2,000 examples and the test set size to 500 examples. Then, we simply take the first 2,000 training samples and their labels, which reduces the overall dataset and allows the model to be trained and evaluated more quickly. We limit the test data to the first 500 images and labels so evaluation runs faster. This subset matches the number of test samples we chose earlier, keeping the setup consistent with our training subset. By reducing the dataset size in this way, we speed up testing while still using a representative portion of the data. The code first confirms that the training and test data each have 3 dimensions, as expected for image data in the MNIST dataset, to ensure the images are structured correctly. It then checks that the number of training labels matches the number of training samples. Together, these checks verify that the dataset has been sliced properly and that every image has a corresponding label before any further pre-processing is done. The code converts the pixel values in the training and test images to floating point numbers and scales them to fall between 0 and 1. It does this by dividing each pixel value by 255, the maximum value in an 8-bit image. This normalization step is important because it helps the neural network process the data more effectively, stabilizes learning, and speeds up convergence during training. The code converts each training and test image from a 2-dimensional grid into a 1-dimensional vector, so it can be used by the dense layers of the neural network. These layers expect flat input rather than matrices, so the images must be reshaped first. Each 28 by 28 pixel image becomes a vector with 784 elements, allowing the network to treat every pixel as a separate input feature. We build a simple Keras sequential model for classifying handwritten digits. The input layer takes a flattened image with 28 by 28 pixels, treated as a single long vector. We then add a dense layer with 64 units and a ReLU activation to introduce nonlinearity so the model can learn complex patterns. Finally, we add a dense output layer with 10 units and a softmax activation, which produces a probability for each of the 10-digit classes from 0 to 9, making it suitable for multi-class classification. In this step, we choose the loss function for our model, which is sparse categorical cross-entropy. This loss is well suited for multi-class classification tasks, where the target labels are given as integers. It measures how different the true labels are from the model's predicted probabilities. By minimizing this difference during training, the model learns to correctly assign each input to one of several possible categories. In this step, we choose an optimizer for training the neural network. We use the Atom optimizer, which is widely used because it is both efficient and adaptable. The learning rate is set to 0.001, a common starting value that balances how quickly the model learns with how stable the training process is. This choice helps the model converge toward a good solution without taking steps that are too large and overshooting the optimum. We create a metrics list that includes accuracy to evaluate the model. This means we measure how often the model's predicted labels match the true labels. Accuracy is simple to use and gives a clear sense of how well the model is performing on a classification task. The model is now being compiled, meaning it is prepared for training with specific settings. It uses the Atom optimizer with a learning rate of 0.001 to efficiently update its weights. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when labels are given as integers. Accuracy is tracked as a metric, so we can easily see how well the predicted labels match the true labels. Together, these choices configure the model to learn effectively from the data. We train the model using the Keras fit method, providing the training data and labels as inputs. The model runs for 3 epochs, meaning it passes through the entire dataset 3 times. We use a batch size of 64, so the model updates its internal parameters after processing that many samples at a time. The verbose setting is 0, so training runs without showing progress messages. Finally, we use a validation split of 10%, reserving part of the training data to monitor the model's performance during training. The code evaluates the trained model using the separate test data to see how well it generalizes to new, unseen examples. It computes the loss and accuracy on this test set with detailed output turned off during the process. These evaluation results are saved as test loss and test accuracy, which can later be used for reporting or further analysis. This code prints the type of loss function and the metrics used in the model. It reads the stored loss name and the list of metrics, then displays them in a clear format. This lets you verify which settings were used when the model was compiled and trained, improving transparency. It also helps with debugging and analyzing the model's configuration. The code reports the model's performance on the test data by printing the final test loss and accuracy. It converts each value to a floating point number, rounds it to 4 decimal places for readability, and then prints it with a clear label. This gives a concise, easy-to-interpret summary of how well the model performs on unseen data. This script walks through a simple machine learning workflow in TensorFlow and Keras, using a subset of the MNIST handwritten digit dataset. It sets a fixed random seed for reproducibility, then normalizes and flattens the images before feeding them into a basic sequential neural network, with one hidden layer using ReLU and an output layer using softmax for multi-class classification. The model is compiled with sparse categorical cross-entropy as the loss, the atom optimizer, and accuracy as the evaluation metric. It is trained for 3 epochs with a batch size of 64, then evaluated on a separate test set. Finally, the script reports the TensorFlow version, the chosen loss and metric, and the test loss and accuracy to summarize model performance. Training with callbacks. Callbacks are important tools for managing model training on real-world datasets because they let you run custom actions at specific times, such as after each batch or epoch. This makes it easier to monitor training progress and decide when to stop. For example, in a medical image classification task, you might stop training once validation performance no longer improves, which saves time and computing resources. Overall, callbacks give you fine-grained control while keeping the training process simple and efficient. Early stopping is a training callback that watches validation metrics such as loss or accuracy and stops training when they stop improving for several epochs. This prevents overfitting by ending training once performance plateaus instead of letting the model start learning noise. Another common callback saves a model checkpoint whenever a new best validation score is reached. This ensures you keep the best version of the model, even if later training makes it worse or is cut off unexpectedly. Callbacks are tools that help you monitor and control model training. They can record metrics and learning rates at each epoch, so you can visualize learning curves and spot problems like unstable training. In practical systems, callbacks may also adjust learning rates or send notifications when training finishes. In research, they support systematic comparisons of different training strategies while keeping other settings fixed. Overall, callbacks make training more flexible, observable, and better suited to real-world needs. Python code. Training with callbacks. This lesson demonstrates how to train a model using Keras callbacks. It uses a small subset of the MNIST dataset, so training runs quickly. The main goal is to show how to apply early stopping to halt training when performance stops improving, and how to use checkpoints to save the best model during training. In some setups, you may need to install a specific version of TensorFlow to keep everything compatible. The comment is suggesting that you install TensorFlow version 2.20.0 using the standard package installation command. Doing this helps ensure the code runs smoothly with the expected library version and avoids problems that can occur with newer or older releases. We begin by importing three Python libraries. The operating system library lets us interact with the system, for example, to check whether files exist. The random library allows us to generate random numbers and set seeds so our experiments are reproducible. Finally, the numerical computing library NumPy provides efficient tools for working with arrays and performing mathematical operations. To make our code produce the same results every time it runs, we set deterministic seeds for our random number generators. We first set a seed of 42 for the random library, so that any random operations using it are repeatable. We then set the same seed for NumPy's random number generator, ensuring that NumPy's random values are also reproducible. This consistency is important for debugging and for reliably comparing results across different runs of the code. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layer components from Keras so we can quickly assemble the different parts of a neural network model. This line displays the version of TensorFlow currently in use. It provides a quick check that the environment is using the intended TensorFlow release. Confirming the version helps ensure that the rest of the code will run correctly and remain compatible with the installed library. The code first checks whether any physical graphics processing units are available using TensorFlow's configuration tools. If a graphics card is found, it sets the device so that computations run on the GPU for faster processing. If no GPU is detected, it falls back to using the CPU instead. This automatic choice of device helps optimize performance based on the hardware that is actually available. The code uses Keras to load the MNIST dataset, a standard collection of handwritten digit images. This dataset is automatically split into a training set, used to teach the model, and a testing set, used to measure how well the model performs. Loading and splitting the data in this way is an essential first step before any pre-processing or model training can take place. The code prints the shapes of the training and test datasets to check their dimensions before any pre-processing. This quick check confirms that the data has been loaded correctly and matches the expected sizes. Doing this is important for debugging and for understanding the basic structure of the dataset before moving on to further analysis or model building. The code prepares the training and test images by converting their pixel values to floating point numbers and dividing them by 255, which changes the range from 0 to 255 down to 0 to 1. This process, called normalization, puts all input values on a similar scale. As a result, the neural network can train more efficiently, with better performance and faster convergence. The code converts each training and test image from a two-dimensional grid into a one-dimensional vector, so it matches what the neural network expects. Instead of a 28 by 28 matrix of pixels, each image becomes a flat vector with 784 elements. This reshaping step is necessary so the dense layers in the model can correctly process the image data as input. In this demonstration, the dataset size is deliberately reduced to speed things up. The training set is limited to 8,000 samples and the test set to 2,000 samples. Using fewer examples makes training and evaluation faster, which is especially helpful for quick experiments or when computing power is limited. The code reduces the training dataset to a smaller subset for faster processing. It keeps only the first 8,000 training images and their labels. This smaller dataset makes the training run more quickly and easier to handle. The goal is to speed up the process, especially for demonstrations or experiments where using the full dataset is not necessary. For quicker evaluation, we use only a subset of the test data instead of the full test set. In this example, we take the first 2,000 test images along with their labels. This smaller sample lets us run evaluations faster, which is especially helpful for demonstrations. The goal is to speed up testing while still showing how the evaluation process works. We build a simple Keras sequential model for classifying min-nis digit images. Each image is flattened into a vector of 28 times 28 pixel values as the input. The model first uses a dense layer with 64 units and a ReLU activation to learn patterns from these inputs. It then uses a final dense layer with 10 units and a softmax activation to output probabilities for the 10 possible digit classes, allowing the model to predict which digit each image represents. In this step, the model is compiled to prepare it for training. The atom optimizer is selected because it is efficient and adapts well to different gradient patterns. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the target labels are integers. Accuracy is used as the main metric to track how often the model predicts the correct class during training and validation. In Keras, we can use an early stopping callback to monitor validation loss during training and stop when the model stops improving. Here, training ends if the validation loss does not get better for 2 epochs in a row. We also enable restoring the best weights, so after stopping, the model automatically returns to the parameter values that achieve the lowest validation loss. This helps ensure the final model reflects its best observed performance on the validation data. We define a file where the best model will be saved. Then, create a Keras model checkpoint callback that watches validation accuracy during training. Whenever the model reaches a new highest validation accuracy, the callback saves it to that file. We configure it to keep only the best version and to store the entire model rather than just the weights. This ensures we preserve the best performing model configuration for later use. We train the model using a fit function that takes the training data and labels, automatically reserving 20% of the data for validation. The model is set to run for up to 20 passes over the data, using batches of 64 samples before updating its weights. We add early stopping, so training stops if the validation loss does not improve for 2 epochs in a row, and a model checkpoint that saves the weights whenever validation accuracy gets better. The training is run in silent mode, so no progress messages are printed during this process. To assess the model's performance, we use the separate test subset that was not used during training. We call the model's evaluation procedure on this smaller test data and its labels, with the settings adjusted so it runs silently without showing progress. This evaluation returns 2 key metrics, the loss and the accuracy on the test set. Together, these values indicate how well the trained model generalizes to new, unseen data. To find out how many epochs were actually run during training, the code looks at the history object returned by the model's training function. This history stores a dictionary of tracked metrics and losses. By taking the list of loss values, where each entry corresponds to 1 epoch, and measuring its length, the code determines how many epochs were completed. This reveals how long training ran before early stopping halted the process. We first report which device was used for training, either a GPU or a CPU, depending on what is available. We then state how many epochs we originally requested. Compare that to how many were actually run with early stopping. And give the best validation loss to show performance on unseen validation data. After that, we present the test loss and test accuracy, both rounded to 4 decimal places, to summarize how well the model performs on the test set. Finally, we check whether the checkpoint file exists to confirm that the model's best weights were successfully saved for later use or deployment. This script trains a simple neural network on a subset of the MNIST digit dataset using Keras with TensorFlow, emphasizing the use of callbacks for early stopping and model checkpointing. It sets deterministic seeds for reproducibility, checks whether a GPU is available, and prepares the data by loading, normalizing, and reshaping it for a dense network. The model consists of 2 fully connected layers with rectified linear and softmax activations, and is trained with the atom optimizer and sparse categorical cross-entropy loss. Early stopping monitors validation loss and stops training if it does not improve for 2 epochs, restoring the best weights, while a checkpoint saves the model with the highest validation accuracy. After training, the script evaluates the model on a test subset and reports the device used, number of epochs run, best validation loss, test loss, accuracy, and confirms that the best model was successfully saved. Model evaluation basics. After training a model, you need to evaluate it on new data to see how well it actually performs. In Keras, when you evaluate a sequential model, it computes the same loss and metrics used during training, but it does not change the model's weights. This distinction matters because training updates the model, while evaluation simply measures its current performance. For example, in a fraud detection model, evaluation on unseen transactions shows how accurately it identifies fraud, giving you a clear sense of its effectiveness before deployment or further tuning. When evaluating a model, it is important to keep training, validation, and test data separate. The model is fitted on the training data, which can make its performance there look unrealistically good. To measure how well it truly generalizes, you should rely on validation or test sets that were not used during training. In practice, you monitor validation performance to decide when to stop training or which version of the model to keep, and then use the test set once at the end to estimate real-world performance. This process helps detect overfitting, where the model memorizes training patterns instead of learning to handle new data. When evaluating a model, you should connect both the loss and the metrics to the real goals of your task. The loss value measures how closely predictions match the targets, but it is often hard for non-experts to interpret. Metrics like accuracy, precision, and recall are usually clearer because they relate directly to real-world consequences, such as prioritizing recall in medical diagnosis to avoid missing true cases. Regularly checking these metrics helps you improve models, compare different designs, and decide when a model is ready to be deployed. Python code. Model evaluation basics. This script demonstrates a simple way to evaluate a machine learning model. It first trains a very small sequential model in a safe and controlled manner. After training, the model is tested on separate data that was held out from training. This evaluation step shows how well the model performs on new, unseen examples. A line that begins with an exclamation mark is a shell command used in a notebook environment to install a specific TensorFlow version, in this case, version 2.20.0. Using this command ensures the code runs with the exact intended library version. This is important for keeping the code compatible and making results reproducible across different runs or systems. The exclamation mark simply indicates that the line should be executed by the system shell rather than as regular notebook code. We start by importing tools that support our model evaluation process. The operating system module lets us interact with the system, for example, to set environment variables or manage files. The random module provides random number generation, which we use to set seeds and make experiments reproducible. Finally, the numerical computing library NumPy gives us efficient support for arrays and mathematical operations. Together, these imports provide the basic infrastructure for data handling and consistent results. To make our code produce the same results every time it runs, we set deterministic seeds. We first fix the seed for the general random number generator so that any random operations behave consistently. We then set the seed for the numerical library's random generator to the same value, ensuring its random outputs are also repeatable. Finally, we set a specific environment variable that controls how Python randomizes hashes, which further improves the overall reproducibility of the script. We start by importing TensorFlow, a library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. From Keras, we import the layers tools, which let us stack different kinds of layers, such as dense or convolutional layers, to define the structure of our neural network model. This line of code prints the version of TensorFlow currently in use. It lets you quickly confirm that the correct version of the library is installed. This check is important to ensure compatibility with your code. It also helps with debugging when something does not work as expected. The code uses TensorFlow to check whether any GPU devices are available. If at least one GPU is found, it sets the device to GPU, so computations can run faster using that hardware. If no GPU is detected, it automatically falls back to the CPU, so the program still runs, just without GPU acceleration. The code prints a message indicating whether computations will run on a GPU or on the CPU. Earlier in the script, it checks if any physical GPUs are available. If at least one GPU is found, it selects the GPU. Otherwise, it falls back to the CPU. This message helps you understand which hardware is being used, which matters because performance can differ greatly between CPU and GPU. We use the Keras Datasets module to load the MNIST dataset, a standard benchmark for image classification that contains images of handwritten digits. The data is divided into a training set and a test set, where the training set is used to fit the model, and the test set is used to measure how well it performs. Each image comes with a label indicating which digit it shows, so we can train a supervised learning model to recognize and classify the digits. We check the shapes of the training data arrays to confirm they match what we expect before training a model. This simple step helps us quickly spot problems like mismatched dimensions that could cause errors later. By verifying the shapes early, we make sure the data is structured correctly and ready for the next steps in the training process. To speed up training, we reduce the size of the dataset by keeping only the first 5,000 samples from the original training data. We apply the same reduction to the corresponding labels, so that each input still matches the correct output. This smaller subset lets us train the model more quickly, while still providing enough data for it to learn useful patterns. To create a small validation set, we take a slice of the training data instead of using the test set. We select the images from index 4000 to 5000 in the training set as our validation images. We then take the matching labels from the same index range as our validation labels. This gives us a separate dataset to check how well the model is performing during training. We are using a smaller subset of the training data to make model training faster and easier to handle. Specifically, we only take the first 4,000 samples from the training set. This reduction speeds up experimentation and testing, which is especially useful when computational resources are limited. It also allows for quicker iterations when developing and refining the model. We first convert the training images to floating point numbers and scale their pixel values to fall between 0 and 1 by dividing by 255. This normalization puts all inputs on a consistent scale, which helps the model learn more effectively. We apply the same normalization to the validation data so it matches the training data. Finally, we normalize the first 2,000 test samples in the same way to prepare them for later evaluation. To prepare MNIST images for a neural network, we first define the input shape based on their size of 28 by 28 pixels. We then flatten each image into a one-dimensional vector of length 784, because dense layers require one-dimensional input. Using a reshape operation, we convert the two-dimensional images into these vectors while keeping the first dimension flexible to represent the number of samples. This transformation ensures the training data matches the expected input format of the model's first layer. We reshape the validation data so that each image is flattened from a two-dimensional array into a one-dimensional vector of length 784, matching the input shape required by the model. We apply the same reshaping to the test data to prepare it for evaluation. This step is essential because the model's input layer is designed to receive data only in this flattened vector format. Before building the neural network, the code checks and prints the shape of the smaller training dataset. This confirms that the data has been reshaped correctly and matches the expected input format for the model. Verifying these dimensions helps prevent errors caused by mismatched input sizes during model construction and training. In short, checking the data shape is a simple but important step to ensure the model will run properly. We build a simple sequential model in Keras for image classification. The input layer takes a flattened vector of image pixels. Then we add a dense layer with 64 units and a ReLU activation to learn patterns from the data. Finally, we add a dense output layer with 10 units and a softmax activation, which produces probabilities for the 10-digit classes from 0 to 9 so the model can make predictions. To prepare the model for training, it is compiled with specific choices for optimization, loss, and evaluation. The optimizer is set to atom, which is commonly used because it works well with sparse gradients. The loss function is chosen as sparse categorical cross-entropy, which fits multi-class classification tasks where the target labels are integers. Finally, accuracy is selected as the main metric to track how often the model's predictions match the true labels during training and validation. We train the model using the Keras fit method, giving it our training data and labels. We set the training to run for 3 epochs, so the model sees the entire dataset 3 times. A batch size of 64 controls how many samples are used before updating the model's internal parameters. We also pass in a smaller validation set to check performance on data the model does not directly learn from. Finally, we set the training to run in silent mode, so it does not print progress updates while it trains. We evaluate the model on a separate validation set to see how well it generalizes beyond the training data. Using the model's evaluation function with the validation inputs and labels, we compute the loss and accuracy on this set. The evaluation runs silently, without printing progress, and the resulting values are stored as the validation loss and validation accuracy, which summarize the model's performance. The trained model is evaluated on a separate test set to measure how well it performs on new, unseen data. The evaluation function is run using the test inputs and their labels, limited to the first 2,000 samples. The verbosity is turned off, so the evaluation runs silently without showing progress. This process outputs the test loss and test accuracy, which are saved for later analysis. This code prints a brief summary of how the model performs. It first shows the validation loss and accuracy, rounded to 4 decimal places to indicate performance on the validation set. It then shows the test loss and accuracy, also rounded, to report performance on unseen test data. Together, these values help you judge how well the model is likely to generalize beyond the data it was trained on. This script shows a simple example of training and evaluating a neural network with TensorFlow and Keras. It sets fixed random seeds for reproducibility, checks for a GPU, and loads a small, normalized subset of the MNIST digit dataset. The data is reshaped and fed into a basic sequential model with one hidden layer using ReLU activation and an output layer using softmax for 10-class classification. The model is compiled with the atom optimizer and sparse categorical cross-entropy loss, then trained for 3 epochs. Finally, it evaluates performance on validation and test sets and prints the loss and accuracy, giving a quick overview of the basic machine learning workflow on a small scale. In this lecture, you learned to construct Keras sequential models with common layer types for supervised learning tasks, configure model compilation settings including loss functions, optimizers, and metrics, and train and evaluate sequential models using model.fit and model.evaluate. In the next lecture, Lecture B, we will go over functional API. Thank you for your attention. See you all in the next lecture.